All right, then welcome back to COMP526 another time. A new unit, fresh topic, even though quite related to the previous unit. We'll still talk about string matching, but this time how to do this in parallel. And this will be a relatively short unit. It just gives you another kind of flavor of string matching and a new perspective on it. And will turn out to be a second somewhat illustrative problem to see how parallel algorithms work for this. Okay, without further ado, what we'll do is see some parallelization strategies that indeed work for a whole class of fairly simple problems. And we'll identify what cannot possibly be sped up further in some cases. So again, these two things are going beyond just string matching, but it's a nice way to illustrate them. And then there's a concrete new method that you haven't seen. There's another string matching method, which is particularly suited for parallel execution. So we have seen quite a few string matching methods in Unit 4. And they were more or less efficient, apart from the brute force method. But all except the brute force method really gained their efficiency from building on the knowledge of the previous guess. Right? The brute force method was kind of oblivious. For each position in the text, it started from scratch. But all the others, what we were doing in many different ways was trying to gain advantage from what we've already learned in the previous position and take that knowledge to the next position in some way or another, sliding forth and back and all these things. Now, if you think about string matching from a parallel perspective, this sounds exactly like poison. What we need for parallelization is that things are data independent, that the next computational step does not depend on the data or the result of the previous computational step. And here we did exactly the opposite. So it seems like for parallel string matching, the sequential methods are worse than what we had before. Okay, someone posted on Campus Wire, is the live stream working fine? Okay, the app is a bit slow. I'll continue with the parallelized string matching in a second. Looks like it's sorted for now. If not, you can still use the Slido Q&A if you want. All right, back to string matching. It looks like all the effort we spend on making the sequential methods faster is to the detriment of parallelizability. And so it looks like we might need new ideas for turning this into parallel. I want to take one modification to the problem just because from a parallel perspective, this is much more natural. String matching in this unit will mean we want to find all occurrences of the pattern in the text. Just if you think about it, finding the first occurrence would necessarily mean some synchronization step after the parallelizing, in parallel finding all the occurrences. And then it's just an additional step after this. So it's kind of more natural to stay with all the occurrences. And if you want, you can still find the first afterwards. But it seems in parallel not to make much, there's not much you can gain from the fact that you want to find just one. Whereas in sequential, it was kind of natural to stop out the first. We'll also assume that the pattern is shorter than the text as before. Otherwise, you don't have to do much. I want to look first at some elementary tricks. And this is the part that goes beyond string matching. It's something that we haven't talked about in the sorting chapter because we were deeply buried into getting sorting methods fast. But in a way, let's start rethinking parallelization from scratch and try to find what is easily doable. And so there's this notion of an embarrassingly parallel problem, slightly cute term that just means it's a problem that's so easy to parallelize, you shouldn't even be very proud of doing it. It's embarrassingly parallel. It's very easy to break into many small subtasks, and they can all be solved independently of each other. I left the definition deliberately vague. There's no quantitative notions in there because I think the term is more of an idea or an abstract concept than a concrete mathematical definition. But a typical example could be the sum of two matrices. So you have two matrices with floating point numbers. You want to add them up. Well, how does that work with matrices? In the outcome, every entry is just the sum of the two corresponding entries. So you could assign one processor, at least on the conceptual level, to each outcome element, and it just gets the two elements from the input matrices and adds them up. That's n squared, if n is the size of the matrix, say it's a square matrix, n squared little tasks, and they're all independent, right? That's embarrassingly parallel in its essence. Then matrix multiplication is somewhere in between, right? The individual tasks, there's some potential overlap, but it's still independent enough. It's overall a little more effort, but you can still, in a sense, independently compute each of the outputs if you want it. And if you can do this, that's the best case for parallelization, because remember Brent's principle, you can, in a sense, just schedule all those little tasks on the processor you really have, one after the other. The other problem we've seen and looked at from the parallel perspective, sorting, is actually not embarrassingly parallel. It's not really clear how in sorting you would break the whole task of sorting the entire list into small little tasks that are independent. But if you look at our algorithms that we designed, there are subtasks that are of this type. For example, the partitioning step in quicksort, where we compare all elements with the pivot element. That's a task that every element's outcome compared to the pivot is independent of the others. So you can do this completely in parallel, and that's exactly what we did. Now, an interesting question is, how about our about our string matching problem? Is this embarrassingly parallel? That was, sorry, wrong direction. And for this question, I haven't really told you enough, or we haven't covered this yet. So there's no way you can know other than your intuition, or maybe you have seen it before. But I want to ask this question now and later compare and ask it again. Just what do you think? What's true for the string matching problem? We had 30 votes for the last question, and we're at 30 now. Well, 31 indeed. Okay, 3, 2, 1, and let me lock this one. So you see the results are different. Okay, can I show you the correct one here and then switch back to this one? Let's discuss what's correct later after I told you. What could be subproblems in string matching? A natural candidate is to take each of the guesses as one subproblem. If you think about it, we want to find all occurrences. Every position in the text could be the start of an occurrence. So we could say each guess is one subproblem, and the task of the subproblem is to check if the guess is a match. Now that's great because these are indeed independent, right? I can try to take advantage of learning from what the outcome was in one guess and apply that to another one, but I don't have to. They're in essence, they're independent. And so I can do all guesses in parallel. And that's not the crappiest way to do it. Let's put it this way. It's also not the final answer, but let's first see what we can do. If you assign each guess one processor, and that just sequentially checks for all the characters, in the worst case, it has to check m characters if these are all matches or all near matches. So you would need m time, parallel time for the matches, and you would need as many processors as there are guesses, so n minus m, right? And that's what's down here. So the work is n minus m, the number of guesses, times m. And that's the same across these other ideas. It's just the parallel time that we can slightly improve. And here it actually depends on the details of the machine. So you should have seen the parallel AND in the tutorials. Or you're doing this week. But I think you've seen this last week, haven't you? Okay, some nods, some defiantly denying. So you can look this up. The connection here is checking whether a guess is a match is really checking if all these characters match. And then it's a match if and only if all the characters match. So that's a big AND. Is this equal? And is this equal? And is this equal? And is this equal? So after the character comparisons, it's the same problem as computing AND of an array in parallel, all the bitwise AND of all the bits in a bit array. And you've seen how to do this in log m time on a crew RAM, and in constant time if you can actually do concurrent writes. And you can even have this strict version of conflict resolutions. So that's all neat. So the parallel time is really good. It's constant. It's the best you could hope for. But remember, again, Brent's principle, you don't usually have as many processes as the text is long. So you also have to take the work into account. And this is essentially n times m as the brute force method. So we know there are better sequential methods. This method will not be work efficient. All right? So what can we do? We can be slightly smarter by saying, let's try to take advantage of the fast sequential methods that we have. And so a way you can do this here is you divide the text into blocks. And it's important that these are not just m long, but 2m. You will see that they're overlapping. So say these are length m. And then the first block is this part. The second block would be this string. And then the third part, this string, and so forth. And now you're finding inside of each of the blocks, you use a fast sequential algorithm. So you use a sequential method like COMP526, say, inside each of the blocks to find all the matches of the pattern inside the block. Now, the time for this will be essentially linear in m, because both this snippet of the text and the pattern are length m, up to some constant factors. So you need that in parallel time. Now, have you found all the matches by doing this? So suppose there is a match somewhere in the text, say here. That's our pattern. It won't be found in the first red one because it only contains a prefix of p. It won't be found in the third, but there's this second that overlaps, and then we know that this occurrence is fully within this red segment, so it will be found in the second block. If an occurrence is exactly aligned with one of these blocks, it'll be found twice. If you want, you can try to be smart and avoid that case by checking the outcomes, I guess, is the easiest. It will only be reported in 2 blocks, in this and in this. So it might be enough to just avoid that. I wonder if it's enough to just make the blocks 2m-1 long, and then we don't have the problem. Then you don't catch all overlaps, potentially. That's a detail that you can solve either way. Either filter out the duplicates or try to avoid them up front. What we achieve with this simple method is parallel time m. That's as here, but we've seen you can do better. The positive side is the work is efficient, because this comes down to n times m, to n divided m times m. That's the number of blocks, right? N divided by m, with a factor of 2 that is omitted in the theta. And each of the blocks takes m work, so the total work is linear in n. Remember, we used to write theta n plus m for the sequential methods, but with the assumption that m is at most n, we know that is the same as linear in n. So why did we obsess with writing this like that in the previous unit? The thing is that if you pre-process the pattern, you might apply the same pre-processed pattern to several texts, and then maybe you don't know at the time of pre-processing the pattern how long the text will be. So you might already have spent the time linear in m, and then you discover, oh, the text that someone's giving you is actually shorter, and you wouldn't have had to do anything, but it's already done. That's why in the last unit, I was a bit more careful and said, in general, whatever n and m are, the time will be n plus m. Here, I'm a bit more sloppy and say, let's only look at the case we're given the text and the pattern at the same time. And if the pattern is longer than the text, we don't bother to do anything. And we have a way to check the length in somehow without iterating through the pattern. And the only interesting case is when the pattern is shorter than the text. And then these are the same. So that last part is a work-efficient method, but it's not perfect in terms of the parallel time, right? And so if I were to ask you the same question again, I'll open a fresh copy so you can see, you can change your vote and we can keep the old result. I'll wait till we have 30, even though the picture is fairly clear now. Okay. If you were quick last time, you would have seen this answer anyway. So why is it, in this sense, embarrassingly parallel only if the text is much, much longer than the pattern? In that case, you can use this second method and break the text into these blocks of length 2m, and can use a work-efficient method and still have an efficient parallelized method, fairly efficient. Whereas if the pattern and the text are roughly the same length, there's not so much you can do. Even these more fancy methods, they look like the parallel time is decent, but then the work is so big, so unless you have many processors, you won't really have much of an advantage. And for this work-efficient method down here, if the pattern and the text are roughly the same length, it doesn't really do anything. It falls back to the sequential method. All right, so let's wrap up what we've seen so far. The elementary methods are simple, and that's always useful. It's always a good thing to have. We could even run them not on a shared memory machine, but on a distributed machine where, well, on a distributed compute cluster or something like this, where each compute node only has a portion of the text, because the problem is local in the sense you only need a segment of the text that's roughly as long as the pattern. You could still do this, and these simple methods would nicely work with that. But we only really get a speed up if the pattern is quite short. Now, what would we like to improve upon this? What can we do on top of that? It would be nice to have work efficient methods, but then improve the parallel time so we get better speed up. And the only way to get that is to get at the matching part. Somehow we have to parallelize the matching process. The idea of breaking the text into little chunks of roughly size m, that looks useful, but unless we parallelize that step as well, we will be stuck with parallel time m. So it looks like we need some new ideas, at least with just black box puzzling together either the brute force method or existing sequential methods. We won't break this m time barrier. And that's what we'll look at next.